The tectonic plates strain against each other here, locked together until the pressure grows too great. Centuries may pass with no apparent movement, a blink of an eye in the lifetime of our planet. But on some occasions, geological time, human time, and historical time intersect. We are passing through the Golden Gate, entrance to San Francisco Bay. Let us see it as it existed more than a century ago. The busiest port in the United States lies ahead. A city built on shifting dunes, on steep hills of ancient rock, and even in places, on the hulls of sunken ships. Magic hour in the magical city by the bay. An evening like thousands before. But for turn of the century San Francisco, the last evening of its kind. Early morning, April 18th, 1906. In this moment, geological time and human time intersect. In the aftermath of the Great San Francisco earthquake, more than 500 city blocks, 30,000 buildings burned to the ground. 3,000 people perish. From the tragedy emerges the scientific study of earthquakes. Scientists can now reconstruct what happened that day. The event started along the San Andreas Fault, 9 miles west of the city, 6 miles beneath the ocean floor. Friction between the tectonic plates has built up strain around the fault. The earthquake occurs when the plates slip past one another, suddenly, rapidly. The entire landscape shifts, causing intense surface shaking, seen here in red. Over the next 90 seconds, the rupture travels north and south along the fault, eventually traversing hundreds of miles. Diving below Earth's surface, we see the area of the rupture, shown in yellow. The area of the rupture and the amount of slip determine the magnitude of the earthquake, its overall strength. Seismic energy emanates outward from the fault, traveling in waves that penetrate the planet's interior. Seismic waves allow scientists to study what lies beneath Earth's thin crust. Imagine seeing a slice through our planet, revealing its rocky mantle, surrounding a superheated metal core. Activity in the mantle drives the motion of tectonic plates above. Heat left over from Earth's formation, combined with the warmth of decaying atoms, softens the mantle rock, allowing it to flow slowly. Heat flows outward, gravity pulls in, and the exchange of energy causes Earth's surface to move. From this perspective, inside Earth, we can see the rigid plates floating atop the denser mantle. these tectonic plates, tightly wedged against one another, always remain in motion. In some regions, plates spread apart, creating new crust. At other locations, plates move toward one another in a slow-motion collision that takes place over millions of years. Deep ocean trenches outline many of these zones, as one plate sinks beneath another. And in a few places on Earth, including California, plates grind against each other, slowly moving side by side in opposite directions. It takes our most sensitive instruments to detect these motions, but over time, they have transformed the surface of Earth. "200 million years ago, the world looked very different. India rubbed shoulders with Antarctica. Buenos Aires lay not far from Cape Town, and Morocco sidled up to Manhattan. The Atlantic Ocean started to open up around that time, beginning in the north. Tectonic plates pulled apart, and new crust formed in between. We can speed up time so that millions of years flash by every second. This change in tempo will allow us to witness geological time from our impatient human perspective. Europe, North America, and Africa split apart first. And as the southern Atlantic opens up, Africa and South America drift apart. The underwater ridge that traces the center of the Atlantic Ocean reveals the location of new crust forming. The youngest sections of the ocean floor lie nearest the ridge, with older, cooler, denser crust near the shoreline. The process appears to occur smoothly from this perspective, but most of the plate's motion takes place in a series of adjustments we call earthquakes. Sometimes minute, sometimes monumental. These events shaped the landscape we recognize today. During the entire history of our species, Earth's continents have looked fundamentally the same. Traveling along the East African Rift, we see an effect of our planet's tectonic engine, with Earth's crust stretched thin over a plume of hot material rising in the mantle beneath, perhaps linked to a more massive upwelling nearer Earth's core. Over the past 6 million years, this region, shaped by tectonics, featured lakes, rivers, and trees. Our human ancestors evolved here, in an environment favorable to the diversification of life and to the preservation of their fossil remains. Research teams from around the globe, including the California Academy of Sciences, continue to make discoveries about early humans in this region. Over many generations, our ancestors migrated out of Africa, establishing civilizations on landscapes shaped by plate movements. In the shadow of mountain ranges with rich topsoil and abundant water, people took advantage of the benefits of living in tectonically active areas. In Cyprus, plate movements lifted up a portion of the sea floor, exposing veins of copper that provided raw materials for the Bronze Age, more than 4,000 years ago. Those same plate movements shook the land throughout the Mediterranean, collapsing buildings and perhaps bringing down whole civilizations. Over millennia, people have built and rebuilt in regions prone to earthquakes, but offering fertile land and precious metals to the inhabitants. These cultures left behind archaeological remains and historical records that help scientists understand ancient earthquakes. But only in the last century have we developed precise instruments to monitor seismic events. The world's tallest mountains, the Himalayas, rise to the left. Underneath, the Indian plate moves northward at a rate of about an inch every year, pushing into the Eurasian plate and causing the Himalayas to rise. The force of this slow-motion impact causes tremors in the surrounding terrain as solid rock fractures and shifts to accommodate the rising mountain range. As a result, the rich agricultural region around Assam, India, has experienced two of the most massive earthquakes ever recorded, in 1897 and again in 1950. In the last century, the concentration of people in urban centers has increased tremendously, increasing the risk to societies built in seismically active areas. In 1976, the 1.6 million inhabitants of Tangshan, China, experienced an event similar to what occurred 70 years earlier in San Francisco, as a fault slipped in a sudden rupture. The city suffered nearly total destruction. At least 250,000 people lost their lives. On March 11th, 2011, the Pacific Plate suddenly shifted beneath the eastern coast of Japan. The rupture resulted in the largest slip ever measured, releasing 60 times the energy of San Francisco's 1906 earthquake. When the locked Pacific Plate snapped free, it lifted a massive quantity of water, causing a tsunami that spread across the entire Pacific Ocean. A computer model recreates the wave's path, revealing complex patterns shaped by features on the sea floor. In 8 hours, the tsunami reached Hawaii, and shortly after, the coast of California. In a very real way, seismic events connect the entire world. And although catastrophes capture our attention, earthquakes large and small happen every day around the globe.
Let's take a minute now and see how those earthquakes are indeed happening every day around the globe. We've taken the last 30 days of earthquake data and mapped it onto our planet. We've done so using a piece of software called Worldwide Telescope, developed by Microsoft Research Laboratories. This is a free piece of software you yourself can download at home, once again, for free. And what we've done is we've mapped not just the location on the surface of the Earth these earthquakes are occurring, the latitude and longitude, we've added in their depth below the surface of the Earth, giving us a point we call the hypocenter of the earthquake. So we're not just looking at these in 2 dimensions, where they are in the Earth, we're looking in 3 dimensions, where they happened inside of the Earth's crust. We've started out here, above North America, where indeed you can see that California is one of the most seismically active parts of the United States. As we fly across the plate, you'll see not a lot happens in the middle of continental plates. Earthquakes occur where plates run into each other, where they connect, where they join. So let's fly to the middle of the Atlantic Ocean and look at that feature mentioned earlier, the Mid-Atlantic Ridge. This is what we call a divergent plate boundary. This is where new crust is being formed in the middle of the Atlantic Ocean. Now, divergent plate boundaries don't have very frequent earthquakes occurring in them. The plates are moving apart, not grinding against each other, not pushing one underneath another. So a lot of earthquakes don't happen here. However, the creation of the Atlantic Ocean, pushing apart the continents, does result in earthquakes. There's only a limited amount of crust on the planet, and as new crust is forming here, it's pushing the continents away from each other. They have to go somewhere, and they end up running into each other and plates on the other side of the planet, creating earthquakes. So as we fly across the Mediterranean, we can see here Africa is being pushed up into Europe, creating the Alps mountain range, and some light earthquakes right now, although many heavier earthquakes have occurred in the Mediterranean. And a little bit further east, we can come to the Middle East and see where some very large earthquakes happened quite recently. There's actually 2 earthquakes we see here at this bright point. These happened yesterday in Iran, not too far from the city of Tabriz. There was a magnitude 6.4 earthquake, followed very shortly by a magnitude 6.3 earthquake. Now, Iran is in part of a very complicated set of plates. We have the Eurasian plate up here to the north. We have the Arabian plate down here to the southwest, and the African plate a little bit further southwest, and not too far away, the Indian plate as well. All these plates are intersecting right here. There's also what we call the Anatolian block, sort of a subplate of the Eurasian plate. So these are all intersecting here in this region near Iran. Now, this part of Iran right here is a lot like the coast of California. It's what we call a strike-slip zone. That means the plates aren't running into each other, they're grinding against each other. And as they grind against each other, they release energy in the form of these earthquakes. So a very large earthquake that happened in Iran just yesterday. Flying a little bit further east across Iran, we can get to western China, where we can find another very large recent earthquake. Now, we saw just a moment ago how the Indian plate is driving up into the Eurasian plate. That, of course, creates the Himalayan mountain range, as the Indian plate is being forced under the Eurasian plate, forcing up the land of the Eurasian plate, creating earthquakes, including this magnitude 6.3 quake that happened in western China just this morning. Now, these places where plates converge, we often call subduction zones. That's where one plate is forced to slide underneath another plate. Usually, denser oceanic plate, such as the Indo-Australian plate here, is forced underneath the slightly less dense continental plate, such as the Eurasian plate here. We can see places where they intersect, like the island of Sumatra here. Now, along the intersections, along these subduction zones, where one plate moves under another, we find these deep ocean trenches. As one plate is forced to dive down into the mantle under another plate, they make a very deep trench in the ocean. A great example of that can be found over here in the Western Pacific, where the Western Pacific here is being subducted under the Philippine Sea Plate. This actually creates the deepest of all the ocean trenches, the Mariana Trench, which goes down to a depth of about 6.5 miles below the surface of the ocean, the deepest part of the Earth's crust. Pretty much the entire Western Pacific is a subduction zone. As the Atlantic Ocean continues to push Africa, Asia, Australia towards the east, they're forced to go somewhere, and so these slightly less dense continents ride over on top of the denser Pacific plate, forcing it underneath them back down into the Earth's mantle. Over the course of millions of years, mile after mile, the Pacific has been forced back down into the mantle, closing it up to what we find today. We can see a lot more ocean trenches as we fly south, including this trench, the Tonga Trench. You can see here, there are very, very deep earthquakes happening here, up to hundreds of miles below the Earth's surface. You got to think that when an earthquake is happening, that's part of the plate down in the mantle being forced further and further down. The Tonga Trench is actually, although not quite as deep as the Mariana Trench, one of the most active sites of plate motion on the Earth. Here, the plates are moving at a rate of about 8 inches per year. Most other parts of the world, they only move about 1 inch per year. Very, very active site of plate motion, but the Pacific plate is being forced under the Australian plate. As we fly across the middle of the Pacific, again, not a lot of activity in the middle of a plate, but coming to South America, we again find a subduction zone. Once again, the opening up of the Atlantic is forcing the continents to go somewhere, and so they're being pushed on top of the Pacific plate, subducting the Pacific underneath them, back into the mantle. The motion of South America over the Pacific has created the Andes mountain range and lots of earthquakes. South America is the site of the most powerful earthquake ever measured, which was measured off the coast of Chile in 1960. As we fly up to North America, there's not a lot of subduction happening in North America. There's a little bit here, where the Cocos Plate is subducting under Mexico. But if we return back to California, you might notice there's no ocean trench along the western edge of North America. That's because nothing is being subducted here. We are instead a strike-slip zone. So the Pacific Ocean is moving one way, North America is moving the other way, and we're grinding against each other. Strike-slip zones don't have as powerful or as frequent earthquakes as subduction zones do, but compared to the rest of the United States, California is very seismically active. You can see there's been a few earthquakes here in the past 30 days, none too close to the Bay Area, one down there a little bit to the east. But of note is this little cluster of earthquakes a little bit north of the Bay. This is nearby Cobb, California, and in Cobb, California, there is a geothermal power plant. Now, geothermal power is generated from the heat of the Earth. It's a place where the crust of the Earth is very thin, so a lot of heat from the mantle comes up, and we can inject lots of water down towards the deep rocks nearby the mantle, heat up that water, make steam, and generate energy. But as we inject that water deep into the crust, it does cause some seismic activity that we can measure as earthquakes, a somewhat unintended consequence of generating power deep inside the Earth. Now let's return to the last part of our show and see how scientists and engineers are making our world safer from earthquakes.
Throughout the western United States, monitoring stations measure the intensity of earthquakes on university campuses and public land, but also in office buildings and private homes. Instruments record and share data about events on a daily basis. Scientists also monitor the degree to which plate motion deforms Earth's surface. Satellites use GPS to measure changes in Earth's geography to within a fraction of an inch. Locked along faults, the crust warps and bends nearby. The amount of deformation can provide clues to the likelihood of an earthquake along the fault. Much of the movement we detect in the Bay Area takes place near the San Andreas Fault. But many faults cut through the California coastal region, forming an extensive network of fractures. The Hayward Fault runs nearly parallel to its more famous neighbor to the west. The Hayward accounts for a portion of the movement between the Pacific Plate and the North American Plate. And it has shifted only slightly since its last great earthquake in 1868. What might an earthquake look like along the Hayward Fault? Scientists use computers to simulate such an event. This simulation depicts one scenario, one possibility. If 50 miles of the fault were to rupture, it would release about 1/16 the energy of the 1906 earthquake. But the resulting shaking intensity depends on many local details. Scientists take into account the proximity of mountains, the type of soil, and other factors to calculate the shaking intensity. Results from these simulations allow engineers to design safer structures for earthquake-prone areas. In fact, we use computers to construct virtual models of the structures themselves to simulate how they will behave when built from concrete and steel. And engineers also conduct tests in the real world. This 3-story structure sits atop a shake table, driven by seismic data from an actual earthquake. The shiny isolation bearing you see here permits the building above to move independently of the ground below. These experiments enable engineers to improve on a design already put to use in San Francisco's City Hall. One of many techniques applied to strengthen the building, the isolators allow City Hall to float above the ground. During an earthquake, the entire building can move more than 2 feet without critical damage. The building's resiliency mirrors the need for a community's resiliency in the wake of a serious event. The original City Hall crumbled in 1906, so its successor must prove more durable. San Francisco's ferry building survived the 1906 earthquake, but it too has benefited from engineering improvements. Recent retrofits have strengthened its familiar tower, much as the building itself, a focal point for busy city life. It strengthens the community in which it stands. Although we experience the world from our own human perspective, we can learn to appreciate the timescales on which our planet evolves. And we can take action, not just in the design of our buildings, but in the fabric of our daily lives.